Today we are going to discuss on a very technical topic, titanium ore campaign for blast furnace hearth repair. This presentation serves as a global consultant quick reference for extending the operational life of a blast furnace through a strategic chemical intervention. We'll explore how to manage hearth erosion effectively using TiO₂ to ensure long-term stability. Our primary objective is to extend the hearth campaign life by anywhere from 6 months to over 2 years without causing significant productivity losses. We achieve this by forming a composite layer consisting of TiC N, slag and iron on the cool wall. This layer acts as a shield and it protects the underlying carbon brick from intense heat and chemical erosion. Success also depends on the staying of mm, uh, within the correct target band, and as this target band is very nicely shown, for good production we aim for a titanium concentration in hot metal between 0.07% and 0.15%, while the formation begins at 0.067%, you must be cautious of the red zone. If titanium level exceed zero point 0.20, you risk creating sticky slag and difficult tapping condition, a state we must avoid, and each one of also aware about this boundary. Now to enter the protect mode, we look at the three chemical markers. First, titanium must be at least 0.074% to ensure saturation. Number one, this is the number one point. The second point is that silicon should be at or above 0.42% to increase titanium activity and suppose deposition, because this silicon is the only material which combine with oxygen present in Ti to take out. So we must have to be sufficient silicon to take out the oxygen of Ti. Finally, sulfur, and this is one of the most important ingredient, and that must have to be within the boundary that should be below 0.061% to avoid competition and enable the growth of TiC N layer. Now, once this sulfur becomes more, then all these titanium will be consumed by sulfur, and in return titanium carbide and nitride targeted our activity will fail. So how much ore do we need? So using 40% titanium ore, we use the formula, that is delta Ti is equal to 0.12 into ore in terms of kg per ton hot metal, that is the titanium ferrous ore. For a standard repair, which is our recommended path, we target an ore rate of 8 to 10 kg per ton of hot metal. This typically result in a titanium concentration of 0.1 to 0.15 in the final hot metal. So it is very near to the it is of course away from the level which we have shown, but here we must have to, operator or blast furnace team must have to be very careful. So then now the timing is everything, as it is our tagline for this activity. Our mantra is 7 days to show, 10 days to grow, and 3 weeks to stay. So during the first week you will see titanium level rise, but thermocouple might stay stable. Don't panic. By day 10 the growth phase begins and crystals form, and you will see sidewall temperature finally start to drop. So to maintain this reaction, we need a hot center and cold wall. Hot center and cold wall are the best combination to segregate two nuclei TiCN on the furnace wall and even in the corners and bottoms of the carbon brick. The central hearth should be between 1500 and 1530 degrees centigrade to keep the titanium dissolved, and for this operators are requested to keep focus on their central points, the apparent central point temperature, very well during the execution of this project. However, near the wall the temperature must be under 1400 degrees centigrade to trigger the precipitation of the productive TiCN layer, or during this operation each one of blast furnace team must be focused on the cooling system of the side wall. Either we can keep the same cooling potential, or if we could able to increase it, then it will benefit in a big way in formation of this TiCN precipitate. We also must aggressively desulfurize to stay within our safety target. So now coming to the slag composition, this slag chemistry is just as vital as metal. We maintain basicity between 1.1 and 1.3 to keep titanium in the slag as TiO₂. We aim for TiO₂ level of 1% to 2% above the baseline. It is critical not to overshoot this level, and if the slag become too stiff with a viscosity over 1.5, it will disrupt the furnace tremendously, and it will hamper the production and productivity. So visually the process works in four steps, and this is very important what we are going to discuss. The hot core carries the dissolved titanium. As that metal reaches the cold wall, the local temperature drop and the metal becomes super saturated. Titanium, carbon and nitrogen then crystallize on the rough carbon surface, eventually building a protective skin between 20 and 100 thick. So the TiC equilibrium solubility curve illustrates why temperature control is our primary lever. In the dissolved region at high temperature, if you see titanium stay in solution very comfortably. So as we move into super saturated region, by cooling the metal near the wall, TiCN is forced to precipitate. So one thing we must have to remember, high basicity pulls Ti to the slag, while low basicity releases Ti to form the protective layer that we have just discussed in the earlier slide also. So we wrap up with our operational roadmap. We start with a pre-visit assessment to collect baseline data. By days 1 to 3, we begin daily ore injection and strengthen cooling. Day 4 to 10 represent the critical phase where we monitor thermocouple for that expected temperature drop, and this is supposed to be one of the most intensive exercises to be conducted, to be operated by the our blast furnace operation team. Finally, after day 14, we gradually reduce ore injection, ensuring the layer stay consolidated for long-term hearth protection.